Hello student, to the Foundation of Classical Electrodynamics course. So, under module 2 today we have lecture 48 and in today's lecture we will continue the few problems regarding the image method that is started in the last class. So, today we have class number 48. And today we will going to continue this image method technique to solve few typical problem. This is also a one kind of boundary value problem and effective when we have a system where we place a point charge near the conductor and try to find out the potential or electric field nearby. And in that case what happened that for example, in the last day's problem we had a coordinate system like this and we had a plane like this and one charge was placed here and it was asked that what should be the, that was the z direction, what should be the electric field at some point at r above this conductor. So, the problem is a bit difficult because in order to understand the potential we need to know the charge here, but also it will going to induce some charge here over this plate, and in order to know the potential you need to know what is the charge distribution, what is the amount of charge induced, etc. So, the problem is simple when you consider a image charge, a fictitious charge that will give us a equivalent effect as far as the boundary conditions are concerned, and as a consequence of the uniqueness theorem we will get the same result. So, that problem we discussed last day. So, we will going to extend this. Now, we have another problem, say example 2. So, in this example here we have a point charge a point charge and a grounded conducting sphere. So, this is the system. So, let us first draw the system. So, we have a conducting sphere like this and suppose a point charge is placed somewhere here. This is the point charge that is placed and this is grounded. So, that means the potential over this sphere should be 0. This is grounded and this is the system. Let us consider the radius of this system to be say a, the sphere a, and it is placed suppose a distance from here to here a distance d. Okay, now let us go back to the problem. So, that is the system I just draw. Now, the problem is this, the problem is find out the potential at some point P whose coordinates are theta and R should be greater than A. So, outside the conductor I want to find out, and it has to be, because inside the conductor the field we know it is 0. So, some point P, what should be the potential? So, let us draw that point P. Suppose this point here is my P, which is a function of r theta, and I want to find out the potential at that point P. And in order to find this potential, now the problem we discussed before last day, that it is partly due to the q, the potential here is partly due to the point charge placed here, say plus q, say this point is A and this is origin O, let us put some name. So, the potential here at point P is due to partly the point charge plus q, which is already there, and due to the induced charge over this sphere. And so, there are two contributions like before. So, instead of having a sphere, now we can consider a image charge, due to which whatever the potential we get, that satisfy the boundary conditions. So, let us assume somewhere here, by just considering the symmetry, somewhere here we have my image charge, and that image charge is say q prime. So, q prime, by symmetry I put this q prime over this line, and this q prime is the effective or the corresponding image charge for which I want to find out. So, eventually I have two charges plus q, and whatever the contribution we have here as a induced charge, I replace everything to this point charge q prime, which is located the line joining to the origin O and the point A, and that is purely because of the symmetry of the system. And whatever the field I will, whatever the potential I will get due to this system is equivalent to the potential I will get due to the placement of plus q charge at q prime. So, q prime is my image charge. Okay. So, now the boundary condition, let us see that this point is a B. So, the boundary condition, which is the most important here, that is why it is called the boundary value problem. The boundary condition is saying that phi at r equal to A, that is over the sphere, the potential is 0, because it is grounded. That is the first boundary condition. What is second boundary condition? The second boundary condition is saying that phi at r tends to infinity has to be 0, and that is the trivial boundary condition, that if I go to very, very far distance, the potential should not be there, because it falls at 1 by r normally this way. So, okay, these are the boundary condition. Now, let us, because now we have 2 point charge plus q and q prime. So, we need to find out what is the distance in terms of this system. So, the suppose this is my theta, and suppose I join this line here from here to here. So, this is, and also I can join this A, and so here this point says C. This point is C. So, the potential here at C point is 0. So, let us one by one calculate. Suppose from here to here this distance is d prime, and this d prime we need to evaluate. Okay, so I just joined the point Q to P, and over this we have a C, and over the C the potential is 0. So let us now write one by one. So what should be my phi at R equal to A, due to the plus charge, plus Q charge and Q prime, it is 1 divided by 4 pi epsilon naught, and then Q divided by the distance from that point. So this is at point C. At point C. So AC and Q prime plus Q prime divided by BC. So that quantity is 0. Now AC and BC I can write in terms of whatever the parameter is there. So let me do that first. So AC, the distance, is simply A square plus D square minus 2A D and angle cos theta whole to the power half. Obviously this is because OC and AC, so this is D, OC is A, so D square plus A square, and this angle is theta, so 2D into A cos theta. So that is the thing I am having here. What about BC? BC is A square plus D prime square minus 2A D prime and cos theta whole to the power half, right? Because now it is this and I have BC, so BC is eventually this point, this length, and AC is this length. So that we are doing in a dotted line. Okay, so now if this is equal to 0, this quantity is equal to 0, that means Q divided by AC is equal to minus of Q prime divided by BC. So that is the condition we are having. So Q divided by AC is equal to minus of Q prime divided by BC. Okay. Now this is true for all the theta value, whatever the theta value you take. So over all this point, over all this periphery, what happened that the value of the potential is 0. So it is true for all the theta values. So now if that is the case, so we can readily see that Q divided by A, let us simplify the expression, and then I take A common, and then 1 divided by D square divided by A square minus of 2 D by A cos theta whole to the power half, and the right hand side I should have minus of Q prime divided by, I take D prime common, so 1 plus A square D prime square minus 2 A divided by D prime cos theta whole to the power half. Okay, this is the condition we are getting. So as I mentioned, this equation should valid for, so this equation is valid for all theta values. If that is the case, then coefficient wise it should be same. So that means q divided by a, I can write minus q prime divided by d prime. So, from that I had an expression of q prime, which is the image charge in terms of the given information, and that is q a d prime. Mind it, d prime is still unknown. And another equation, if it is true, then the ratio of this cos theta has to be same, and also this one. So, d by a, these things should be equal to a by d prime. So, from here I have another equation that d prime is equal to a square divided by d. Okay. So, now q prime I can know explicitly in terms of all the known quantity. So, q prime is simply becomes minus of q divided by a, and d prime I calculated, it is a square divided by d. So, it is minus of q and a divided by d. So, that means this is the amount of induced charge or the corresponding image charge if I put here at the distance d prime, where the d prime is also calculated, that it is a square divided by d. Then the first boundary condition, that the potential at r equal to a should vanish, is satisfied. So, that means I satisfy the first boundary condition with this, and also with this potential you can see that the second boundary condition, we will see that how the second boundary condition can also satisfy it, because it is 1 by r form. So, potential, so I know now the q prime and all these things. So, what should be the potential at r, that I need to write. So, hence the potential at p r theta at the point P, which is potential at the point P function of r theta, that value is how much? Phi r theta is equal to 1 by 4 pi epsilon naught, and then it should be q divided by this distance, mind it. Now, this is from here to here, from here to here. So, this distance I can write in terms of r and theta and d, and it simply comes out to be this r square plus d square minus 2 r d cos theta whole to the power half. That is the that is for the charge q, and for charge q prime is q a divided by d. So, I simply put it divided by r square plus d prime square. Now, d prime square also we know what is d prime. D prime is a square divided by d, this quantity. So, this is my d prime. So, I will put it here, a to the power 4 divided by d square, and okay, then minus sign, not plus, then I have a minus sign, 2 r, and then a square divided by d and cos theta whole to the power half. That should be my potential, and you can see that for this potential both the boundary condition is satisfied. So, the boundary condition again I should write the first boundary condition, phi at r equal to a is 0. If you put r equal to a here, then you should see that this quantity has to be 0, and also second one, phi r tends to infinity 0, because if you put r tends to infinity here, then you can see that the phi is 0. So, both the boundary condition is satisfied. So, that means if I have a structure like this, a conducting sphere, and if I place a charge nearby, and then if I want to find out what is the potential at some point p, that potential should not be simply q divided by 4 pi r, rather this is this one, this is this one. Okay. With that satisfying these two boundary condition, that is the main thing. Well, now we like to check the potential is there. Now, exploiting the value of the potential, we like to check that the induced charge that we calculated is really the value of this quantity or not, q a divided by d, this value or not. So, in order to understand that, so our standard technique is first to find out the surface charge density. So, first we calculate the surface charge density, and after that what we do, that I will calculate the total charge. So, the surface charge density, how the surface charge density will going to change, because I am placing a plus q charge here. So, the surface charge density over this surface will going to change, and that we first calculate. So, this is regarding the calculation of induced charge. So, before going to calculate the total induced charge, let us find out the surface charge density, which seems to be a function of theta, because it will not the surface charge density may not be uniform over theta, and that quantity is minus of epsilon 0 del phi del r evaluated at the point r equal to a. This is the standard expression we are using from last class onwards, and we know that why it is, because the electric field very near is sigma divided by epsilon 0, which is minus of del phi del r in this case. So, from that we know the expression is this, and that is over r equal to a over the sphere. So, now phi we know, because I just calculate phi. So, we know what is del phi del r. So, that we need to calculate. It is exactly like the previous problem. So, if I do, then sigma theta should be equal to minus of 1 by 4 pi epsilon will going to cancel out, and then derivative with respect to r of this quantity, this first one, this one. So, first we need to make a derivative of this one, and second we need to make a derivative of this one. So, if I do, I will get say minus of half, and then q was there, and then I have 2 of r minus d cos theta divided by whatever the term we had there, r square plus d square minus 2 r d cos theta whole to the power 3 by 2. That is my first term. What is my second term? My second term is minus q a divided by d, and then again I have another minus half here, like, and then simply r minus a square divided by d cos theta, and then multiplied by 2 multiplied by 2 whole divided by whatever we had, r square plus a to the power 4 divided by d square minus 2 r s square divided by d cos theta whole 3 by 2. Looks a very lengthy calculation, but very straightforward. Okay, evaluated at r equal to a. Okay. Now the next thing is at r equal to a, what is the value? So r equal to a, so that quantity gives us 1 minus of 1 by 4 pi, and then I just replace r equal to a, and if I do, it should be minus q multiplied by a minus d cos theta whole divided by a square plus d square minus 2 ad cos theta, just replacing r to a 3 by 2, and then plus of q a divided by d, and then a minus a square d cos theta whole divided by a square plus a to the power 4 divided by d square minus 2 a cube divided by d cos theta whole to the power 3 by 2. Okay. Now now this next term q a divided by d multiplied by a square d cos theta divided by that quantity let us simplify, because if I not able to simplify, if I not going to simplify it, then I am not going to do further. So if I only consider this term and simplify, so let us do that first. For this term I have q a divided by d, and then I should write a minus a square divided by d cos theta. What is there, I just write it. Denominator I will make a change, I say write a cube, I take common d cube. If you take this, then I have say d square plus a square minus 2 a d cos theta whole to the power 3 by 2. So you can check it that whatever we had written is correct or not. So we have one a cube, and also so here we just, so okay, this is nothing here. Okay, so from the denominator I just take the just take this common, whatever I take common is, I need to make this 2 ad, so that means I take 1 by d common, and also I take root over of that thing, no, the square of that thing. So if I do that, then I have 3 by 2, so this 3 by 2 become this quantity. So I just take a square divided by d square common. So, from here I just take a square divided by d square common and I will get this. Okay, so I mean, what is the point of having this? The point is I can have the denominator both the cases same, this one and this one. That is the reason why I did it. So, let us simplify this more. So, if I put this upward, then I simply have q and this d goes to upward. So, I should have d square divided by a square and then multiplied by a minus a square divided by d and cos theta whole divided by a square plus d square minus 2 ad cos theta whole to the power 3 by 2. Now, we are set. Now, we are set because we are in a position to calculate, because the denominator is same. So, my sigma now becomes sigma theta is minus of 1 by 4 pi, and I should have minus of q a plus q d divided by cos theta. I just simplify the first here, this one q a minus q a and then take a, no, not divide, why I make divide, it is just q d cos theta, I just multiply, right. Okay. So, it is just q d cos theta, that is the first. What about the second term? Second term sounds like plus q d square divided by a, and then minus of q a square d, so q d cos theta. Okay, one thing we are getting here, and in the denominator I have the common denominator, that is a square plus d square minus 2 a d cos theta 3 by 2. So, what I do here is I just simply cancel, these things will simply cancel out, and eventually what I am getting is this minus of q divided by say 4 pi 4 pi a, and I have d square minus a square here divided by a square plus d square minus 2 ad cos theta 3 by 2. That is the value of the theta we are having. Now, you can see that the charge density is not independent of the theta. Note, the induced charge density, the surface charge density sigma function of theta depends on, very much depends on the value theta. So, that eventually that means that I have this sphere here and the point charge was sitting here, but the charge density depends on theta. So, whatever the charge density we are having here at theta equal to 0, at this point the charge density is different. So, the surface charge density is varying over this theta because it is a function of theta. Now we can find out what is the maximum minimum. So we can readily do that. So let us do that as well. So sigma max, that if I calculate, then it has to be the value when the denominator is minimum, and denominator will going to be minimum when we have, this is like this is like a minus d whole square. So if that is the case, so I have q divided by 4 pi a, and we have here in the numerator we have d square minus a square. So I can write it d plus a into d minus a, then just this d minus a is going to cancel out by 1 d minus a that we are having in the denominator. So it should be d plus a divided by d minus a, and it has to be square because it is cube. So this has to be square. So what is then minimum? So minimum happen when the downstairs is maximum. So that means it is minus of q by 4 pi a as usual, and then we have d minus a, because now in the numerator we have d plus a square, d plus a and square of that. So this is the way it is distributed. So that means when theta is equal to 0, we have a minus b whole square. So that means the induced charge will going to be maximized when we have the point here. This is the point we have maximum, and this is the point when theta is equal to pi, then cos theta will be plus 1, cos theta will be minus 1, and the numerator it will be a plus a minus d whole to the power 3 by 2 here, this point. So that gives me the minimum point here, the minimum distribution. Well, I know I can now find out the total charge because the total distribution is in my hand. So the next thing is to find out what should be the total induced charge. So that is the final verification, that the total induced charge q, that has to be integration of sigma, which is a function of theta, and ds. This is the technique we also used in the last problem, but here we should note that q prime, that was the induced charge, we already figure out the value to be minus of q a divided by d, right, and that we should have here q a divided by d, that value you should that should be equivalent to the image charge. So that is the image charge we calculated, and now you calculate the total induced charge q by exploiting sigma, and this sigma I calculated from the potential that is calculated. So that is some sort of cross verification we are making, and let us find what value we are getting. So my ds should be a square sin theta and d theta d phi, and my q should be, say a square is constant, so I can take it outside, integration 0 to pi sigma theta, then sin theta d theta, this is the integration of theta, and I should have another integration 0 to 2 pi, and that integration is over d phi, but there is a phi symmetry, so I should have simply 2 pi out of that. So I simply write it as 2 pi a square. Now my integration, let us explicitly write my sigma. It is 0 to pi, and it is minus of q d square minus a square divided by what sigma we get. This is the sigma we are getting, this is the sigma we are using. So my sigma theta is this quantity, minus of q d square minus a square. 4 pi a is there, so I can put this 4 pi a outside, say I should write is 4 pi a, and then I have a sine theta which is already there. In the denominator I have a square plus d square minus 2 ad cos theta whole to the power 3 by 2 and over d theta. Okay. So this quantity is simply minus of, so 2 pi 4 pi will give me 1 by 2, so it should be minus of q, and then 1a will cancel out, d square minus a square will come out, and I should have a 2 in the denominator, that is this quantity, and then 0 to pi, the integration, we simply have sine theta d theta whole divided by this term, a square plus d square minus 2 a d cos theta whole to the power 3 by 2. Okay. Now let us write change of variable. X consider as a square plus d square minus 2a d cos theta. If that is my case, then in terms of x the limit will going to change. So when theta goes to pi, x goes to a minus a plus d square, because from here, but when theta goes to 0, x goes to d minus a whole square. This is the limit. Dx, if I calculate, it should be 2a d sine theta d theta with a negative sign. No, already the negative sign is here, so I should have a plus sign here. So eventually my q is minus of q a, then d square minus a square divided by 2. Now this is dx is this quantity, so 2ad, so I just put an extra 2 ad here, and then I integrate, so this become my dx then, and in the denominator I have simply x 3 by 2, and the limit will be a minus d whole square, and the upper limit will be a plus d whole square. So this is how much? Minus of q a, then d square minus a square, then 4 of ad, and I have a x to the power minus half, and in the denominator I have minus of half. That will be evaluated at a minus d whole square or d minus a whole square and say d plus a whole square. So, this is, so this half 2 minus sign will going to absorb. So, we have q divided by, so 2 will be there, so 2 and a is cancelling out here. So, we have q divided by 2d and then d square minus a square, and for that limit I have 1 divided by a plus d minus 1 divided by d minus a, that is all. So, this quantity is q divided by 2d d square minus a square, and this quantity is d minus a minus a d this is d minus a minus d. So, I should have say in the denominator I have d square minus a square, and here we have 2a, d will going to cancel out. So, we have 2a with a negative sign. So, that thing is cancelling out and 1 2 will cancel out. So, whatever I get is q a divided by d with a negative sign. Now, this is equivalent to q prime, that is our equal to, this is the image charge that we consider. So, we cross verify that the image charge can be calculated from the potential with this direct calculation. It is a lengthy calculation, but just to show that whatever the procedure you are doing is proper or not. So, I have already my time is already up here today. So, I just try to show a couple of problem regarding the image method, the complete problem. So, I suggest the student to please do the boundary value problem by from some standard book, and with the help of the knowledge that you gain in last 2 or 3 class, you just need to apply that on that problem to find out it. The problem generally little bit lengthy, but it is very important for your understanding that how the methods are working. So, with that note I like to conclude my class here. So, see you in the next class. Thank you.